Hello and welcome to the walkthrough of the August 2015 New York State Regents Chemistry exam. This is a walkthrough of Part C. The first batch of questions you encounter in Part C are grouped as questions 66 through 68. Two naturally occurring isotopes of antimony, antimony 121 and antimony 123, are provided for you, and there's a table here that gives the identity of the isotopes with their atomic mass values and their natural abundances. A little bit more information is provided, and also an equation showing a reaction between antimony sulfide and oxygen, producing another type of antimony oxide and sulfur dioxide. Three questions associated with this information. The first one is going to ask you to calculate a percent composition from a formula. Second question will be asking you to calculate the atomic mass using a weighted average technique. And the third question, balancing an equation by inspection. Let's go to question 66. Number 66. Determine the percent composition by mass of antimony in the compound referred to as stibnite. And they've given us the gram formula mass of that compound is 340 grams per mole. The stibnite, from the reading section, antimony and sulfur are both found in the mineral called stibnite, and there's the actual formula of stibnite, Sb2S3. Referring to the formula for calculating percent composition from table T of the reference tables, we see that the composition by mass is going to require that we know the mass of the part we're looking for, divide that by the total mass of the compound, and multiply by 100. Since antimony has a formula mass of 121.8 grams per mole, and there are two antimonies in our formula Sb2S3, the total mass contributed by this part, the antimony part of the compound, is 244. So dividing the 244 by the total mass of 340, then multiplying by 100 to generate a percentage computation, we wind up with 71.8 roughly. The Regents is going to accept a range of numbers here depending on where you've rounded numbers off, but we're just going to stick with what we got, 71.8, and that'll be just fine. Question 67. In the space provided in your answer booklet, show a correct numerical setup for calculating the atomic mass of antimony. This is a weighted average computation. Don't just add the numbers together and divide by 2. That's how you would get an average if the two materials had exactly the same distribution of mass. But they don't. You can see that the two varieties of antimony, antimony 121 and antimony 123, they have different masses and they also have different levels of abundance. So the way we calculate this is we're going to be multiplying the individual atomic masses by the percentages of their natural abundance, and then we're going to add those values together to get our actual average. So we set up the computation. For the antimony 121, it's going to be the 120.90 times the decimal equivalent of the percentage, which is 57%, which changes to 0.57 on the decimal equivalent. And we're going to add that value to the antimony 123 contribution, which is 122.90 times 0.43, the decimal equivalent of 43%. Now, as you notice, they've only asked us for the correct numerical setup, so you need not go any further. Just give us the setup. Question 68. Complete the balancing of the equation in your answer booklet for the roasting of stibnite using the smallest whole number coefficients. They've given us the equation, and they've left some blanks for us to fill in to balance the equation. They've also provided us with one of the coefficients in this balancing process. So if we find out where the arrow is in our equation, we need to make sure that we have exactly the same number of each type of atom on the left side of this equation as we have on the right side. So where do we start? Well, let's go with this 2 that they've given us because they've locked us up with that number. The antimony, since there are 2 antimonies in the compound, 2 times 2 is 4. So without a doubt, we need to have 4 of the Sb antimony atoms on the left side and the right side of our equation. That forces us on the right-hand side. You see the only location for antimony is right here. So we have to put a 2 in this space. We're locked up on that. We don't have any choice. Similarly, for the sulfur, we have 6 sulfurs over on the left side of our equation. So we have to represent 6 sulfurs on the right-hand side. That forces us to multiply the single sulfur that appears in this product by 6. So we have to put a 6 in that space. Now let's add up all the oxygens. We have 2 times 3, or 6 oxygens in this space, and then 2 times 6, or 12 oxygens in this space, for a grand total of 18. So we have to represent 18 oxygens. You can see that they occur in pairs, so we are forced to put a 9 in front of the oxygen part of the equation. And that's it. So the correct balance in this equation, you need to have a 9 in front of the oxygen, a 2 in front of the Sb2O3, and a 6 in front of the SO2, and then your equation is balanced. Next up is question group 69 through 72. Here we're given a laboratory investigation where our lab workers dissolving ammonium chloride in water, and they follow a procedure, a 4-step procedure, and they're recording observations for each step in the procedure. We won't go through all the little details that are here until we need to. Ammonium chloride is dissolved in the water. The laboratory procedures and corresponding observations made are recorded here. We're going to be asked to do 4 things with this information. First, we have to discuss the bonding forces that are present in the compound being dissolved. Then we're going to be asked to describe the properties of the saturated solution that's formed, describe the energy changes involved in the dissolution process, and finally describing the effects of temperature on the solubility of this compound. So, let's get started with question 69. Question 69. Identify 2 types of bonds in the solute. The solute is the NH4Cl, the material that dissolves into the water. I've put together the Lewis dot structure for this compound, and the Lewis dot structure, because we have NH4Cl, we know there's a polyatomic ion present. That's the ammonium polyatomic ion. I've constructed that. There's your nitrogen with 4 hydrogens, and this polyatomic ion is held together by 4 covalent bonds. These are 4 single covalent bonds existing between the nitrogen and the individual hydrogens, all together forming a positively charged ion, the ammonium ion. So we do have covalent bonding present within the polyatomic ion. But that ion is held together with the chloride ion because of the fact that they have opposite charge. So there's a static electric charge difference here that holds the ammonium to the chlorine, and that type of bond is called an ionic bond. So the 2 types of bonds present in the solute are covalent and ionic. Question 70. State evidence from the investigation that indicates that ammonium chloride solution is saturated. Well, let's see what we're doing in this process here. First, we measured the temperature of 10 milliliters or 10 grams of water, put it into the test tube. We've added 5 grams of the solute. We stir the contents, and then we measure the temperature again when we're finished after 4 minutes. Here's what happened. At 25.8 degrees, the ammonium chloride settled to the bottom of the test tube. We stirred, and a small amount of the ammonium chloride remained at the bottom of the test tube. So this water in this test tube has dissolved all the ammonium chloride that it possibly can at this temperature, and there's still a little bit that remains undissolved. That's our evidence that we've saturated the solution and we have a little bit extra left over. So I'm going to put that as simply as possible, which is to say some of the NH4Cl remains undissolved. There are other ways you could word that, but our evidence is here in observation number 3. So we have to kind of translate that into our own terms. Question 71. State evidence from the investigation that indicates the process of dissolving NH4Cl in water is endothermic. Well, an endothermic process is one that absorbs energy from the surrounding environment. Now, if the ammonium chloride being dissolved absorbs energy from the surrounding environment, which would be the water itself, we should see the temperature of the water decrease. And we do. See, we start at 25.8 degrees, and at the end, our temperature is 11.2 degrees Celsius. Put in simplest terms, the temperature of the water decreases. Question 72. State the observation that would be made if procedure 3 is repeated with the original temperature of the water at 98 degrees Celsius. To help us with this question, let's take a look at the solubility curve table, table G from the reference tables. The experiment is being done at 25.8 degrees. That's down in this range of the graph, and you can see that our compound, our solute compound, ammonium chloride, at 25 degree range has a solubility of roughly 40 grams per 100 grams of water. If we raise the temperature all the way up to 98 degrees, the solubility of this substance increases dramatically. It would far exceed the amount that we're trying to put into the solution. So we would have a solution that would no longer be saturated. It would be able to hold a lot more solute. The result of this would be that when you stir it, that would be procedure number 3, if you stir the contents, the observation would be that no amount of ammonium chloride would remain at the bottom of the test tube. So that's what we're going to write for our answer. No solute remains undissolved. Question group. Questions 73 and 74 revolve around a very short narrative which describes the combustion of pure carbon in the presence of sufficient oxygen to produce carbon dioxide as the only product, and heat being given off by the reaction. We're going to do two things with this. We're going to draw a particle diagram that shows the phase of matter of one of these materials, and also we'll be asked to identify the features of the potential energy diagram that might be associated with this particular equation. So let's go to question 73. For question 73 in the answer booklet, we're going to use the key to draw at least 5 particles in the box to represent the phase of the product. Our product is carbon dioxide. Notice it's in the gas phase, and a carbon dioxide molecule has this appearance. And because it's a gas, our 5 particles are going to be drawn randomly somewhere in this space. So we'll locate them. They can be pretty much anywhere. 1, 2, 3, 4, and we'll put one over here in this little corner. The key thing to remember here is that the particles all have to be drawn the same way. This will be fine. And they also cannot be touching each other. That would suggest that they are liquid or solid, and they're not. So exactly where you draw them in the box really doesn't matter, but they should be not touching each other, and they should try to represent showing them occupying the entire space within the box. They are a gas. So this is the particle diagram of a gas. Question 74, on the potential energy diagram in the answer booklet, draw a double-headed arrow to indicate the interval that represents the heat of the reaction. They've drawn a potential energy diagram in your answer booklet that shows our reactants, carbon and oxygen, and our product, carbon dioxide. So we start the reaction at a certain level of potential energy, represented by this dotted line, and we finish at a lower potential energy level down here where the carbon dioxide is. Now we have to show the heat of reaction. So we need to know what the heat of reaction is. Just referring to this graphic, this is a potential energy diagram. And the heat of the reaction is the difference between the reactants and the products in a reaction. So it's going to be the distance from where you started to where you ended. Going back to our diagram in the answer booklet, that's the difference between this section of the graph and this section here. So we'll just put arrowheads on that. It doesn't matter where along this interval you draw this, as long as you get the double-headed arrow to fit between these two dotted lines, you have correctly isolated the heat of reaction, the difference between the reactants and the products. Question group for questions 75 and 76. We have a narrative here which describes putting salt on icy roads in the winter. This is going to have to do with solubility and colligative properties of solutions. One New York town requires that a mixture of sand and salt be used on the roads that's 25% or less of sodium chloride by mass. So we're going to also be asked here to analyze a sample and see if it meets up with the rules of this one New York town. So two questions involved. The first one, we have to be familiar with the colligative properties involved here, and the second one, we're going to deal with the percent composition and interpret that in the context of the narrative. So let's go to question 75. Number 75, state in terms of freezing point why sodium chloride is part of the mixture put on icy roads. When you dissolve a solute into a solution, which is what you are doing here, because the sodium chloride will dissolve in the water, but when you do that, you're going to actually lower the freezing point of the newly formed solution. So the ice water that is on the highway will have a lower freezing point. Therefore, it won't freeze, and hopefully that'll keep the roads safe for everybody. So our answer is the addition of sodium chloride to the mixture lowers the freezing point, and I'll abbreviate freezing point with FP, of the salt water on the road. So the key is lowering of the freezing point. Question 76. Explain in terms of composition by mass why the mixture from which the analyzed sample was taken should not be used on residential roads of the town. Well, the town has a rule that the mixture cannot have more than 25% of the sodium chloride by mass. So let's calculate what it does have. It has 3.3 grams in every 10 gram sample. So From table T, the percent composition is calculated as mass of part divided by mass of whole times 100. So 3.3 grams out of 10 grams times 100, that's 33%. Clearly this number is greater than 25%, so we're going to write our answer as the percentage of sodium chloride in the mixture is greater than 25%. Now you can put more detail in there if you want. You could actually say that the percentage is 33% and that exceeds the rule, or you can just leave it at this. Questions 77 and 78 are grouped together with a narrative. We have a laboratory investigation where we have two solutions being mixed together. One is a lead nitrate solution, the other is a sodium iodide solution. This is going to react in a double replacement reaction. And you might think this is going to be a question about double replacement reactions, and knowledge of that is certainly helpful, but they're going to ask us to identify the insoluble compound using table F, so we got a little bit of reference table material, and then also solving a conservation of mass problem, which is a lot more simple than you're going to think. So let's take a look at question 77. Question 77, identify the compound produced that is insoluble in water. So we're checking on the lead iodide and the sodium nitrate. Want to figure out which one of these is not soluble. So we'll go to the solubility guidelines for aqueous solutions. This is table F in your reference tables, and we'll try to find the different pieces. Our two compounds are lead iodide and sodium nitrate. So first, let's check the lead iodide. If you look on the left side of this chart, you won't see any mention of the word lead, but you do see a reference to halides. That includes iodine. And it says that those compounds will be soluble except when they are combined with, and there's lead. So we've got our winner. It's the lead iodide is going to be insoluble in the solution. But let's just double check the sodium nitrate. Sodium is a group 1 ion. It's right there. And it's always soluble. There are no exceptions. Also, nitrate has its own space in this chart. Nitrate is always soluble with no exceptions. So it's going to be the lead iodide. Go back and write in our answer. All we have to do is write PbI2 in the space, and we have our answer. There were only two possible answers to begin with. It was either going to be PbI2 or NaNO3, because those are the compounds produced. Question 78. Determine the mass of sodium nitrate that is produced. As you read through the narrative, you get three pieces of information that relate to the masses of the compounds in this reaction. First, 13.2 grams of the lead nitrate. They tell you have 12 grams of the sodium iodide. So the reactant side of this equation has a grand total of 25.2 grams of material. Conservation of mass tells us that that 25.2 grams is still going to be in the container, and you are told that 18.4 grams of that is in the form of lead iodide. So the remaining mass has to bring us all the way up to 25.2. So if we solve for x in this equation, we just have to subtract the 18.4 from the 25.2, and you'll get 6.8 grams, and that is the answer. Questions 79 and 80 are going to be organic questions, and we have a pretty lengthy narrative with two very complex looking compounds, and they have names you've probably never seen before. Two organic compounds can be represented by their molecular formula C10H18O. In other words, they have exactly the same molecular formula, but you can see their structures are very different. So we're going to be asked to identify the compound classification based on a recognition of a functional group hiding in their structure, and then to explain solubility factors that might be related to their molecular polarity. So we have organic question and also a solubility question from Unit 7 going on here. So let's go to question 79. Number 79, write the name of the class of organic compound to which both of these compounds belong. Well, look carefully through their structures. There's one telltale item that appears on both structures, and that's the hydroxide group OH. Now, due to the presence of this group, we know that both of these compounds belong to the alcohol family of compounds. And if you don't remember where to find that information, it's on Table R. Table R will give you a good representation of all the different functional groups. So because of the presence of that functional group, these are both members of the alcohol family. Question 80, explain in terms of molecular polarity why these two compounds are nearly insoluble in water. The basic overriding concept here is the idea that like dissolves like when we talk about solubility, and water we should have a very clear understanding of water's basic properties, mainly that water is a polar molecule. So it's going to favor the dissolution of other molecules that are also polar. So the fact that these don't dissolve in water tells us that they don't have similar polarity to the water. So we're going to say that water is polar. These compounds are generally nonpolar. That's what we're saying about their molecular polarity. So they have a different molecular polarity than water does, being less polar than water. Our next pair of questions, 81 and 82, come from the acid and base unit. And we have a narrative here explaining gastric juice in the human stomach. So we're going to the human stomach, and we know that the gastric juices have a pH that's given to us. And we're talking about antacids, in this case magnesium hydroxide, used to neutralize excess hydrochloric acid in the stomach. And they've given us an equation showing how that happens. We're going to be asked to predict the products of this acid-base neutralization equation, and also explain the effect of ion concentration on the pH of a solution. So we're going to get into the pH system as well as explaining the neutralization process. So let's go to question 81. Question 81, complete the equation in your answer booklet by writing the formula of the missing product. So we have this equation repeated in the answer booklet, and we're going to be asked to figure out what goes in the empty space in front of the little aqueous symbol there. So this being a neutralization equation, we know that acids plus bases will produce salt plus water. We've got the water, so what we're looking for is some kind of salt. Water comes from the combination of the hydroxide portion of the base and the hydrogen portion of the acid. So if we take those two things away, we're left with magnesium and chlorine. So our missing part is a combination of magnesium and chlorine. Recall from the periodic table that magnesium is a +2 ion and the chloride ion is a -1. We do a little crisscross here to figure out the formula. It's MgCl2. So our missing part is magnesium chloride, MgCl2. Don't miss the two chlorines. And you can double check this. You can see that it's a balanced equation with 1 magnesium and 2 chlorines, 2 times the Cl's. So all our missing parts have been found. Question 82. Describe the changes in both hydrogen ion concentration and the pH of the gastric juice of a human after ingesting this type of antacid. So the acid has a high concentration of hydrogen ions. Adding the antacid to it will cause the hydroxide ions in the antacid to combine with the hydrogen ions of the acid to produce water. In other words, we're eliminating hydrogen ions from the solution. So the hydrogen ion concentration will decrease as the antacid is added. Now, because the concentration of the hydrogen ion is being reduced, we would see that the pH will actually go up, because remember, pH is calculated as the negative log of the concentration of the hydrogen ions. And that's the key there, negative log. So as the concentration of the hydrogen gets smaller, this value will actually get larger. So the pH will increase as a result of adding antacid. Our final group of questions has the longest narrative that we've seen on the test so far. It talks about early scientists exploring the area of oxidation and reduction. We have 2 equations associated with this narrative, and we talk a little bit about how the definition of oxidation has changed over time, and we have very specific examples here of oxidation and reduction processes. 3 questions. We need to use our own reading comprehension skills to explore here what the meaning of oxidation has undergone over the years. Secondly, we have to determine the oxidation state of a particular element in the context of this reading. And third, we're going to be asked to write an oxidation half reaction. So let's go to question number 83 and get started. Number 83, state why early scientists classified the reaction represented by equation 1 as oxidation. Well, you don't have to read too far to find the answer to this one, so I'm going to highlight the important information. Early scientists defined oxidation as a chemical reaction in which oxygen is combined with another element to produce an oxide of the element. So we can use either one of those statements as the root of our answer here. So let me go with the first one. These are reactions in which oxygen is combined with other elements. Oxygen is combined with other elements. We could also use the second part of this. Oxygen or oxides are produced as a result of these reactions. So either way you want to go will work. You might even find other ways to word this. Question 84, determine the change in oxidation number of carbon in equation number 1. I've brought equation number 1 into the picture for us so we can look carefully at it. And we're looking at carbon. We have to isolate what happens to the oxidation state of carbon. Now, as you recall, there are rules for how to find the oxidation state of an element in a compound, and they're somewhat complicated and they're pretty lengthy here. I have to assume that you're ready for the Regents exam. This is definitely something you'll want to study and get good at and practice. So let's see how to apply some of these rules to the carbon. In the first compound, we have a combination of carbon and hydrogen, and we don't really have a set rule for carbon, but we do have a set rule for our hydrogen. It turns out that hydrogen, according to rule number 5 here, is positive 1 in compounds unless it is combined with a metal, in which case it is negative 1. So hydrogen is plus 1 in hydrochloric acid, but negative 1 in lithium hydride. The only metals that can really turn hydrogen to be negative are going to be strong metals. Carbon is not one of those. So in this case, your hydrogen is actually plus 1. And since there's 4 of them, that means that the carbon in this case must actually have a charge of minus 4. So we're starting as minus 4. On the other side of our equation, we're in the compound carbon dioxide. Again, no set rule for carbon, but oxygen has a rule. Rule number 6. Oxygen is usually negative 2 in compounds. There are very specific exceptions to this. They include when we are using a peroxide or when we're combining with fluorine. So we're going to go with a negative 2 for the oxygen in the carbon dioxide. Since there are 2 of them, we're going to have our carbon be positive 4 in this case. So the change that carbon will exhibit in this reaction is from negative 4 to positive 4. And finally, question number 85. Write a balanced half reaction equation for the oxidation that occurs in the reaction represented by equation number 2. So here's equation 2. Before we can tell who's being oxidized, we need to isolate all the oxidation states of all the elements involved. Magnesium and sulfur, both being uncombined, have oxidation states of 0 in the reactant side of the equation. On the product side, magnesium is a group 2 element, so it's plus 2, and the sulfur then is minus 2, so they cancel out to have a neutral compound. So magnesium is going from 0 to plus 2. That requires a loss of electrons, and loss of electrons is oxidation. So our half reaction has to start with magnesium, and we have to have a magnesium plus 2 on the other side, and we're going to be losing 2 electrons, so we have to put our electrons into the equation as well. This is the best answer you can write, and there may be other ways to represent that, but this is the way we're going to show it. And that concludes the walkthrough of the August 2015 Part C New York State Regents Chemistry Examination. I invite you to look up the other parts of this exam, and thank you for watching. Find additional videos at alchemtutor.com. If you have any questions, comments, or wish to ask permission or any kind of help or advice, feel free to email me at asnyder@alchemtutor.com. Thanks for watching.